given, here that's showing the full system, you will have to also either look up or provide a problem statement to account for each of those minor losses. So in this problem, all those are given to you. In your homework, you will have to use chart or figures or table to estimate what those K values are. So for the sharp entrant, the K is relatively high of 1.0. For that owl, the K is about 0.4, not 2.4 is the loss coefficient for those 9-degree owls. And they're geometry dependent, so as you go through your homework, you have to make some decision as to what value to use. A gate valve opened all the way at relatively small K value of 0.16, and at the exit, with no attempt to smooth the exiting flow, is K value of 1. So all those are table lookup. So with that, I can now launch and finish the problem, and it doesn't take that long. Because the Moody diagram losses is the same old calculation we have done of getting the Reynolds number. So the velocity in this water system is about 18 feet per second. From that, the Reynolds number. It's not up to a million yet, it's only about 3 times 10 to the power 5th. But nevertheless, it's obviously a turbulent flow. You can check all these numbers yourself. The roughness factor based on the diameter is about 0.003. So that is sufficient to put me on the Moody diagram, of which I will read and look up. And I want you to verify this at home. The friction factor approximately is about 0.026. That's close enough. The 5 at the last digit is not critical. So up to this point, nothing new. Let me stop and make sure you understand this. Can you do this? Yes?
Is that like weird shape V dynamic, this guy?
Yeah, I almost forgot this. So what's this guy? Anyone want to remind me? So it will save you the time in calculation in the test, because instead of looking up viscosity and then the density, what is this? No. What is kinematic? Yeah, how is it defined? Reference to the viscosity? Mu over rho. So just a very convenient fluid property that's given also in the appendix, in addition to the viscosity. So it just saves you a step. So at times, this is more convenient. Okay, so the energy equation, which I hope is not too challenging. I'm afraid I may be a little short of time. So where would you want to apply your energy equation for the start point and the end point? I hope this is a trivial question. Because energy equation of point 1 and point 2 on that diagram, where do you pick point 1 and where do you pick point 2? I hope this is the obvious answer. 1, far away from the intake, not influenced by the pump action. And 2, always, again, far away from the exit. So my energy equation I'm now adding a new term, which accounts for all those components that can increase my losses. And the summation sign, meaning I have to add them all up. And the shaft work, since this is a pump, is negative. And that sign is important to account for. I think I better change the subscript to make them more consistent. So any question on this energy equation? I hope you can see the simplification very quickly. Pressure drop because they're both ambient. Velocity at the surface of the tank are so large that they're negligible. So when I'm done, my pump head consists now of 3 contribution, 20 feet of water due to elevation change. Remaining all is a function of the velocity, both in terms of Moody diagram and the so-called loss coefficient, so I can num them all up. And if I use all the values on my far left, my Moody diagram losses is equivalent to about 1 within this parenthesis, but the so-called minor now is so deceiving. It's 4 times. 4 times that of the frictional losses due to shear. Because if you add up all those K, and there are 4 pieces of them, inlet, exit, 2 elbows, and a valve, that is 4 times more than the Moody diagram. So the word minor is very, very deceiving. It's not minor, it's the big part of the losses. If you neglect that, you won't get the right answer. So the final head loss, all inclusive, is about 85 feet, 20 feet of which is gravity. The rest is divided 20% friction, 80% due to those added components. Lastly, to get the power, again, that's the end result we want as an engineer, hydraulic engineer, is to size the pump. Would be the same equation let me write it out so you hopefully get more comfortable with using it. M dot, which is now rho Q or rho VA, and the specific work, which is now given equivalently by gravity times the headwise due to the pump. And that will be, when you do all the numbers in horsepower, accounting for the 70% efficiency of the pump, the denominator, the brake horsepower, is what I'm after. And when you go through the numerics, it's about 6 horsepower. 6 horsepower. And for this kind of estimate, as an engineer, you really don't care whether it's 6 horsepower or 5.5 or 6.5. You go buy a pump, you probably don't find something that's exactly 5.55 horsepower. Right? So for the spirit of an estimate within 5–10% accuracy, you're done. You're done. But if you're building an aircraft engine, you won't be done. You can't be good enough within 5% or 10%. You got to be good enough within 1%. because the plane won't fly. You have overestimated all these frictional losses. Yes?
Yeah, what is the B in efficiency?
The B is a layman term in the industry that is referred to as the brake horsepower, which is the actual power consumption if you account for the inefficiency of the pump. Okay? So it's not typical use in engineering, but is used in industry. Questions? So what is the takeaway about the word minor losses? What can you tell me about, is this minor losses really minor? No, by far no, not at all. In most cases, like pumping water or HVAC, there's a significant, big part of the whole power requirement, by far. So I want to cover the last topic, which is how one deal with a long circular pipe. But before that, let me just tease you with a question. What if you have a flow system, the diameter of water pumping are not the same? Let's say for some reason you have a 7 centimeter gasoline piping and you have to step it up or step it down to different diameter. How do you work that problem? Do you know what I'm asking?
How do you account for the minor losses as you change?
Okay, for one thing, when you change that expansion or contraction, there's some minor losses associated with that. But I'm not even asking that. How would you use the Moody diagram to estimate frictional shear head loss when you have a flow system that half of the pipe is 7 centimeter, the other half is 9 centimeter?
The average, take whatever.
Are you sure?
Change due to length for that one.
For each segment of the constant diameter pipe, you have to recalculate a Reynolds number. Right? Because the velocity is different between 9 centimeter and 7 centimeter. Let's say for that 9-mile pipe, 4.5 mile is 7 centimeter, and the other half is 9 centimeter. You have to recalculate a velocity and a Reynolds number and a friction factor for each of those segments. And then you add them up to get the total power, total pressure loss. Do you get it? Yes?
What if you didn't have discretized sections?
Say what?
What if you didn't have like discretized sections and you just had like a continuous narrowing? Then you do.
No, that's a different problem. If you have a pipe that is changing in diameter over a long length, I don't know why people want to do that, because it's a very expensive pipe. Then you have to, you may not even be able to use the Moody diagram accurately, because the friction factor is changing all along the pipe. Yeah, I mean, the approximation is you can divide the different segment and try to get some estimate. Yep.
So would the segments change diameter, would you have minor losses?
Yes, you do. And we will look at some of those too. When you go through a 7 to 9 diameter or 9 to 7 diameter, there will be some separation of the flow and that will create pressure loss. Yeah, there's expansion loss or contraction loss. Okay? So why would anyone want to build a pipe that is not circular? So you have a rectangular HVAC ducting. You know?
You can ship this ducting a lot easier.
You ship it cheaper and also you can build cheaper than a circular pipe. So for a lot of air conditioning applications, you don't have a circular pipe always, but instead there are circumstances that the pipe may be rectangular. All this, without saying, is constant density. And again, the background of this is empirical. And what I mean is you take all the background we have developed for the circular pipe flow, Moody diagram, and you create a new concept called hydraulic diameter. And I'll define that momentarily. obviously the hydraulic diameter has the same unit as length, meter of B, but the circular pipe, the diameter is the same as the hydraulic diameter. But for rectangular pipe or duct, what that is 4 times the cross-sectional area, A, divided by the perimeter, P. In very seldom cases, sometimes the P can be the wetted perimeter. That will only happen not with air, but maybe with water, and the rectangular duct that is also only partially filled with the water. But that's such an exception, I don't want to spend much time on it. So with this definition of so-called hydraulic diameter, now I can use all my same concept of Moody diagram by simply doing one task, which is I will replace for the circular pipe what I have for circular diameter D. Now I just replace that with the new concept of a hydraulic diameter. And all the equation I used before will hold. So the Reynolds number, etc., will be calculated based on this new concept. So as an example, for circular pipe, you would expect this to be the same as the actual geometric diameter, and indeed, when you put in the perimeter and the area and go through that definition of hydraulic diameter, that's exactly what you will get. That's just consistent. No more, no less. But the real application is in the rectangular duct. So let me give an example of that. I will be short of time to go through the question on the homework because I do want you to have sufficient time to do the quiz. So please, for those who have problem with the homework, please read the poster solution. And Tuesday we'll make sure we have sufficient time to go over each and every old homework to prepare you for the test. All right? So a rectangular duct of size B times H, B being the width and H being the height. So that's the cross-sectional area which we are interested in for a rectangular air conditioning duct. The area, simply the product of the width times the height. Perimeter is 2 times the width and the height add together. So now I have from that a hydraulic diameter for a rectangular duct. Based on that definition. So you will calculate now an equivalent hydraulic diameter and use it to replace the diameter for the circular pipe. Yes?
Could you raise the board, please?
I'm sorry, this is the one I cannot waste. I should be more careful next time. Yeah, this is diameter, hydraulic. In the numerator is 4 times, just like we defined in here, 4 times the area, which is B times H. And the denominator is 2 times the width and the height add together. Now all those are intuitive, I hope, with one caveat. And then I will stop right after this last detail which is needed for doing your homework. So while I have this so-called hydraulic diameter, one thing that is at times confusing is when you deal with continuity equation. Where you have to calculate an average velocity, whereby you need an area to do that. Which area will you use in calculating this area? I'll give you 2 choices. Cross-sectional area. Continuity based on the concept of hydraulic diameter. which one represent the physics better.
Cross-section.
Cross-section, correct. This is purely for the use of Moody diagram. So you don't need that for your homework. You will use the actual fluid cross-sectional area, because that's what the water or the air will see in getting the airfish velocity in the pipe. So I've given you all the information needed to do the next set of homework. And next time, on Tuesday, please come prepared with a list of questions, because if you don't, I will lecture. So with all the time left, please start your quiz now.
Just do it. Do it.